Hi everyone, I'm Neslihan Gugumcu. I'm an assistant professor at the Izmir Institute of Technology in the Department of Mathematics in Izmir, Turkey. And I'm currently on leave for a postdoc position at the University of Göttingen in Germany. And today I'm going to talk about knotoids and some related notions to knotoids, including the notion of a braidoid. And mainly I will talk about the results given by Thrive and also our joint results with Lou Kaufman and Sofia Lambrou. So just before starting my talk, I would like to thank to the organizers for this nice invitation and for giving me the opportunity to have an interesting experience of a virtual talk. So let's start with the question, what is a knotoid diagram? A knotoid diagram is basically an open-ended knot diagram that can be considered in the plane or in the two-sphere or in an oriented surface in general, with two endpoints that can lie in different regions of the diagram. By regions of the diagram, we mean local planar components that are complementary to the given diagram. For example, here we picture two knotoid diagrams, and in the first left-hand side knotoid diagram, we see that the endpoints of the diagram lie in the same region of the diagram. And in the second example, the knotoid diagram has its endpoints in distinct regions of the diagram. So the definition of a knotoid diagram is due to Thrive, and it was given in 2012. A knotoid diagram, K in an oriented surface sigma, is a generic immersion of the unit interval into the surface sigma. And by generic immersion, we mean that the mapping K has only a finite number of transversal double points. And we endow each double point with some under or over data, and we call them crossings of K, just as we do for knot diagrams. And also the images of the points 0 and 1 of the unit interval are taken to two disjoint points in the surface under this map K. And they are also distinct points from any of the crossings of K, and we regard them as the endpoints of K and call them leg and the head of K respectively. And any knotoid diagram comes with an orientation. K is oriented from its leg to its head. And we assume the Reidemeister moves on knotoid diagrams lying in some surface sigma to generate an isotopy relation over this set. The Reidemeister moves take place in local disks, and the local disks contain these portions of the diagrams, and they modify our diagrams in a given way, just as in the classical way. We need to be careful just while defining the Reidemeister moves. We assume that the modification disks are free of any of the endpoints of knotoid diagrams. Actually, we forbid to move an endpoint over or under a strand, a transversal strand. By allowing the Reidemeister moves and the isotopy happening in the surface, we define a knotoid to be an equivalence class or an isotopy class of knotoid diagrams in that surface sigma. And we can extend the definition of a knotoid diagram in the natural way. We may define a multi-knotoid diagram. Here is a picture of a multi-knotoid diagram with two components. Apparently one component is a knotoid diagram, which is the trivial knotoid diagram, and the other component is the trefoil knot diagram. And we define a multi-knotoid diagram in an oriented surface sigma to be a generic immersion of just one single oriented unit interval and the number of oriented circles. Again, we endow each intersection and self-intersection of the components of a multi-knotoid diagram to admit an under or over data. And we assume the same set of isotopy moves generated by the Reidemeister moves, and the isotopy moves happening in the surface sigma, and we define a multi-knotoid to be an equivalence class of multi-knotoid diagrams considered up to this equivalence relation generated or isotopy relation. And we could also extend the definition to a linkoid diagram, actually, to have more than one knotoid components. But for the aim of this presentation, we will restrict our attention at most to multi-knotoid case, and we will be working on the knotoids lying in the two-sphere and in the plane. So let's make a comparison between these two objects, spherical and the planar knotoids. Actually, any knotoid diagram given in the two-sphere can be considered in the plane in a natural way. And oppositely, if you are given a planar object, a planar knotoid diagram, we can naturally consider it in the two-sphere by the immersion of the plane into the two-sphere. But while this consideration induces us a surjective, well-defined map, this map is not injective. Here are two examples of knotoid diagrams. When we consider them in the plane, we can show that they represent some non-trivial objects of the plane, some non-trivial planar knotoid types, classes. We can show the non-triviality by using some planar knotoid invariants given by trie, for example, three-variable bracket polynomial, an extension of the bracket polynomial to planar knotoids. But when we consider these diagrams, these objects in the two-sphere, they get trivialized. We can see it easily here. For example, let's focus on the left-hand side diagram, and we can just take a small portion here of the diagram, and we can just drag the small portion of strand through the two-sphere and bring it back to the diagram by crossing it over the infinity point. And then it will be easy to see that we are left with just randomizer one move available to undo the diagram. And this very similar procedure goes on for this object here. So this tells us that we have actually two different theories, planar knotoid theory and spherical knotoid theory. And actually, when we consider our objects, knotoid objects in the plane, we have a more refined theory. We have more knotoid classes in the plane. So we have some geometric interpretations for knotoids lying in the plane and also in the two-sphere. Here, let's start with the picture. We see some planes here and some knotoid diagrams lying in the planes. Let's consider this plane as the XY coordinate plane embedded in the three-dimensional space. And let's determine the two parallel lines passing through the endpoints of the given knotoid diagram and are perpendicular to the XY plane. Here I draw these lines here. And by just pushing the underpassing strands of the given knotoid diagram in the vertical direction to the lower half space and the overpassing strands to the upper half space in the vertical direction. And by allowing the endpoints attached, remaining attached on the two parallel lines determined, but by moving them up and down along the lines, we obtain a collection of space curves, open-ended space curves corresponding to the given knotoid diagram. Here is just one example of the space curve obtained by doing this operation. And in the opposite way, if you are given a smooth, open-oriented space curve, we can just pick up one plane in the three-dimensional space. Suppose that we chose the XY plane, and we determine the two parallel lines passing through the ends of the space curve and perpendicular to the chosen plane. And we can take a projection of the space curve along the lines, so that the resulting object in the plane is a plane curve with some self-intersections, and at each self-intersection we record the information of the weaving of the space curve as under or over, so we obtain the crossings of the knotoid diagram, resulting knotoid diagram. So in this picture we see that two different projection planes chosen result in different knotoid diagrams, obviously. And actually we can show that these objects differ when we consider them as knotoid types as well, knotoid classes as well. I mean, for example, if you compute the bracket polynomial of this object here, of this knotoid diagram, we will see that it's not the trivial knotoid. To obtain a corresponding isotope relation over the space curves corresponding to the knotoid isotopy in the plane, we define line isotopy. Sorry. So we say that two open space curves with their ends attached on two parallel lines are line isotopic if there is a smooth ambient isotopy taking one curve to the other curve in the complement of the lines. And we want this line isotopy to be taking endpoints to the endpoints of the second curve and taking lines to the lines. So we fix the lines and the endpoints are on the determined two lines, and we just deform our space curve in the complement of the lines given. So line isotopy suggests us to work with a chosen, with just a particular plane to go to the knotoid in that plane. And actually, we have a bijection between the set of knotoids lying in some plane and the set of line isotopy classes of smooth open-oriented curves in the three-dimensional space. Another geometric interpretation was made by Thrive for spherical knotoids. First, we define a connected sum operation for the spherical knotoid diagrams. Here, I draw the first summand of the connected sum is a larger diagram and the second summand is a shrinked diagram here. And I just tie the second knotoid diagram from its leg, from its initial point to the terminal or the head of the first summand diagram, to the first diagram. This defines a well-defined operation for the spherical knotoids, and actually it makes our set of spherical knotoids an algebraic, to have an algebraic structure. It becomes a semi-group with identity, but it's not commutative. So Thrive observed that we can relate a knotoid diagram given in the two-sphere to a simple theta graph or theta curve. A theta graph is simply a graph embedded in the three-dimensional space with two vertices and three edges valent to these two vertices. So it's a trivalent graph in three-dimensional space. And the simple theta graph is a theta graph with two of its edges here, the lower and the upper edges bound a disk in the three-dimensional space. And we relate the knotoid diagram to a simple theta graph by just tying the knotoid diagram to the middle edge of the simple theta graph. So here is just a very simple illustration for this knotoid diagram. We tie it to the E0 edge of the corresponding simple theta graph. So theta graphs also, simple theta graphs give us an algebraic structure with the vertex multiplication defined on them. And actually, Thrive showed that the monoid of the spherical knotoids is just isomorphic to the monoid of simple theta graphs given by the vertex multiplication. And we have an obvious connection between knotoids and classical knots embedded in three-dimensional space. Actually, when we have a knotoid diagram, we have two available connections for the endpoints to obtain a classical knot diagram with an orientation on it. Here is an example. We start with the same knotoid diagram, and in the first picture, we choose to connect endpoints, tie the endpoints with an underpassing arc, shown in red. And in the second example, we tie the endpoints with an overpassing arc. And we see that the resulting diagrams represent different knots. Actually, this is representing a trefoil knot, and this is representing the unknot. We have an available Reidemeister 2 move here, and then we will be left with the Reidemeister 1 move available to undo the diagram. And these closures or connections suggest us well-defined maps from the set of knotoids, either in the plane or in the two-sphere, to the set of classical knots. But to have a well-defined map out of these connections, we need to fix the connection type, either with an underpassing strand or overpassing strands, as the results differ. So I give here the definition of an overpassing closure, defined by choosing the connection arcs going underneath everything that it meets during the connection. So these closures suggest us, as Tribe observed in his paper, that some computational-wise complicated knot invariants can be computed over knotoid representatives of that knot. So if we are given a complicated knot diagram, we can just delete one underpassing strand from that diagram to obtain a knotoid diagram. And since we have the underpassing closure as a well-defined map, we can consider the resulting knotoid diagram as a representative of the knot type that we are working with. Actually, to one classical knot, we obtain a collection of knotoid representatives, because we can delete different underpassing arcs from a given diagram, or we can work with different diagrams of the knot obviously. But it is also apparent that knotoid representatives may have less crossings than the knot diagram representatives for the classical knot, so that we can compute some knot invariants that can be computable on diagrams via knotoid representatives. And it really eases our lives, since we get less crossings in knotoid representatives. Tribe in his paper showed that we can do it for knot group, for example. He just applied the Wirtinger presentation directly on knotoid diagrams. He defined a combinatorial knotoid group, and he shows that the combinatorial knotoid group for a knotoid is the same value with the knot group of the knot that this knotoid here, K, is representing. So knotoids can be worked for representing classical knots and for computational reasons, for making the computations less complex. But also knotoids can be thought to be worked for their own sake. Actually, we have a well-defined injective map from the set of classical knots to the set of spherical knotoids. And this map is induced by just deleting an open arc from a given from a given diagram of a knot with an orientation on it. We delete an open arc from the given diagram, but we don't want this arc to contain any crossing, so that we obtain some knotoid diagrams in the end with endpoints lying in the same region, as we show in this picture. We can show that this operation induces a well-defined map when we go to the classes of objects. It wouldn't matter where to cut our diagram, as long as the arc does not contain any crossings, and it wouldn't matter with which knot diagram we start with for the classical knot. So we can show it, it's a well-defined map. And with the injectivity of this map, we say that the theory of knotoids in the two-sphere is an extension of classical knot theory. I should note here that this map is not anymore well-defined when we define the map into the set of knotoids in the two-plane. With the same reason that we have seen some planar knotoid examples that are just trivial in the two-sphere, but they're non-trivial in the plane. It can be shown easily. So actually, with this injective map, we can divide the set of knotoids in the two-sphere into two types. Knot-type knotoids and proper knotoids. Knot-type knotoids are the ones that lie in the image of this map alpha, and proper knotoids are not coming from a knot, they don't lie in the image of this map. Here are some pictures. Obviously, the trivial knot diagram is obtained by just cutting out an unknot diagram. And here's another representation of this knotoid here. What we can say is that the trivial knotoid is a knot type knotoid, obviously. And also we observe that we can give a representation for a knot type knotoid with a diagram whose endpoints lie in distinct regions. So while it's coming from a knot, it's not necessary under the isotopy of knotoids. It's not necessary that the endpoints lie in the same region of the diagram for all representations, for all diagrams of that knotoid type. It should be clear that there is an Reidemeister 2 move here available to bring the endpoints in the same region. And for proper knotoids, since they are not coming from a knot under this map, any diagram of a proper knotoid will have its endpoints in distinct regions of the diagram. So actually, I just wrote that this represents a proper knotoid. Here we have no possibility to bring the endpoints in the same region under the isotopy of knotoid diagrams. But we need to prove that, and it will be clear in the next slides. It will be proven why we can't do that. We need some more tools to show that this is really a proper knotoid. And these two types suggest us a complexity invariant for knotoids that we call the height of a knotoid. Tri defines the height of a knotoid diagram as the minimum number of crossings created by the underpass closure. And the height of a knotoid as an invariant is defined to be the minimum of the heights taken over all equivalent knotoid diagrams to a given knotoid diagram K. We have an obvious observation here. A knotoid has 0 height if and only if it's a knot type knotoid. And this is equivalent to say a knotoid has non-zero height if and only if it's a proper knotoid. So how do we compute the height? It's comparingly easy to see the height of a diagram. Actually, we see the heights of these diagrams. In the first one, we need at least one crossing to connect the endpoints created. And in the second diagram, when we connect the endpoints, we need at least 2 crossings. We could have more crossings if we choose some other connection arc, for example, detouring around the plane or the sphere and bring it back to the other endpoint to create more crossings. But we need at least 2 for this diagram. But for the knotoid types that they present, that they represent these diagrams, we can't say anything right now. We are not really sure that under the isotopy, knotoid isotopy, we could bring the endpoints to the same region of the plane or the 2 sphere. And we are not sure that we can reduce the height here to 1 or even 0. So we give an estimation for determining the height of a knotoid via some virtual knot invariants. One of them was the arrow polynomial that was introduced by Luke Kaufman for virtual knots initially. Then we applied the definition to knotoid diagrams to obtain an invariant of knotoids in the 2 sphere. Let's see how we define it. So we have the oriented state expansion of the bracket polynomial to construct the arrow polynomial. Actually, we do the crossing expansion in the same way of the bracket polynomial. We smooth out any given crossing in the A and in the B type with the same conventions of the bracket. So here we smooth out this crossing in the A way. It will give us the horizontal smoothing, and the B type smoothing will give us the vertical smoothing. The difference from the bracket expansion is that we have orientation on our diagrams to obtain this expansion. We keep the orientation of the diagrams. We don't ignore it. So when we keep the orientation, we see that one of these smoothings, one of the smoothings A or B would result in oriented smoothing, a smoothing that is compatible with the orientation of the local picture here. And the other smoothing is not compatible with the orientation of the diagram. So these oriented smoothings result in a pair of cusps in our local pictures, as we show here. These are just combinatorial expressions for cusp-like structures. And here's a negative crossing. We smooth it in the A and B type again, and the horizontal smoothing is the B type smoothing here. So I recorded this smoothing as A inverse, as a coefficient, and the vertical smoothing is recorded as A, since it is the A type smoothing. It comes from the A type smoothing, and we have this disoriented smoothing here from the vertical smoothing. And also, as in the bracket case, each circular component would contribute to the arrow polynomial with the value of minus a square minus a to the minus 2. So we assume some reduction rules for this cusp-like dots or structures on the resulting state components. After smoothing out each crossing for a given knotoid diagram, we will observe some zigzags formed by cusps, and we want some of the zigzags to be reduced. We want to keep some of them. So what is the rule for reducing some of the cusps or zigzags? For example, let's see the first picture. So any cusp-like formation here divides the plane locally into two regions. One region is spanned by the acute angle here. We call it the inside of the cusp, and the other side is the outside of the cusp. And if a pair of cusps here, as shown, has insides in the same side of the segment we are working with, of the same side of the component, then we eliminate these cusps and we assume it as the trivial arc. And if the insides of the cusps lie in different sides of the segment, we just keep them. So here are some more concrete examples. We have two cusps on a circular component here, on a circular state component. And we can see that the insides of these cusps lie in the same region of the plane. So that we just assume this component is isotopic to the unknot component. And here is another concrete example. We have two cusps on a long state, a state containing the endpoints of the knotoid diagram. So the cusps have insides lying in the same local side of the segment, so we just eliminate them. But here in these pictures, we see that the cusps have insides in opposite sides of the segment, so we just want to record them as new variables. So if we have a pair of cusps on our long state component, we record it as lambda1 variable, and if we have two pairs of cusps, we record it as lambda2 variable. And if we have n pairs of cusps, we record it as lambda n variable. So I should tell here that I won't show it in this presentation, but you can go to our paper with Luke Upman, new invariants of knotoids, that by a simple argument coming from the Jordan-Kerr theorem, we can show that none of the circular components would have any cusps under the reduction rule. So any cusps would be eliminated if we see them on circular components. So we define the arrow polynomial as an extension of the bracket polynomial. So we define it as a summation over the states that we obtain by smoothing out the crossings of a diagram K, of a knotoid diagram K. So we have the usual vertex weights here, just the multiplication of the coefficients coming from the smoothings of the crossings, A's and A inverses in the corresponding state. And we have the loop value here, and the power is the number of the loops minus 1. And we have the extra variable lambda i's corresponding to a long state with I zigzags or I pair of cusps, let's say. They are irreducible zigzags. And in this form, the arrow polynomial is a regular isotopy invariant. It's invariant under the second and the third Reidemeister moves. But for obtaining a knotoid invariant, we normalize it with the right term, with the same term for the normalization of the bracket polynomial. Here I gave the term. So we obtain a knotoid invariant. Here is a computation after these definitions or notions, abstract notions. We see the knotoid diagram here that I claim to be a proper knotoid in the former slides. So we smooth the two crossings in both possible ways to obtain 4 states here. So in the first case, we smooth the crossings both in A way. So we record the smoothing sides with a coefficient here, A square, and we obtain this trivial arc as the state component. And in the second and the third and the fourth one, we see some zigzags on the state components. And for the second and the third one, we can see that the cusps have insides in opposite sides of the segment. So we keep them as a new variable. Since we have a pair of cusps, so we will keep this long state component as lambda 1, contributing to the polynomial. And here in the fourth case, again, the long segments cusps have different have insides in different sides of the segment. So we keep this long segment component as the variable lambda 1. But we have the circular one with cusps whose insides are lying in the same planar region. So we record this as the loop value, D. And when I sum this up, I obtain the arrow polynomial here. So here, one thing that we need to note here now at this slide is we observe a new variable here, lambda 1. Corresponding to this zigzagged irreducible long state components. And I need to normalize this polynomial to obtain a knotoid invariant. So in this slide, we prove that this knotoid diagram does not represent a trivial knotoid, the trivial knotoid, sorry. So what we have shown is that the lambda variable of the arrow polynomial gives some information about the height of the corresponding knotoid. So let's define the lambda degree of the arrow polynomial. It is the lambda degree of a summand of the arrow polynomial of a knotoid that is in the form a to the m times lambda I is equal to the I. And the lambda degree of the arrow polynomial of a knotoid is defined to be the maximum lambda degree among the lambda degrees of all summands of the polynomial, obviously. So we can show that the arrow polynomial of a knot type knotoid has 0 lambda degree. So if we compute the arrow polynomial for a knot type knotoid, we will observe no lambda variables. It would actually correspond to the bracket polynomial of that knotoid. So this can be proven with a similar observation with the fact that circular components are free of cusps under the reduction rules. The same logic applies here for proving that. And we have shown that the height of a knotoid in the two-sphere is greater than or equal to the lambda degree of its arrow polynomial. So the lambda degree is a lower bound for the height of that knotoid type. So with this result, now I'll go back to the slide. With this result, I can deduce that since we obtain this arrow polynomial here and the arrow polynomial has lambda degree 1, I can deduce that this knotoid diagram is representing a proper knotoid with height 1. Actually, its height is lower bounded by one, but since we could represent it with a diagram that needed to be closed with just one crossing, we can deduce from here that this knotoid diagram really represents a height 1 knotoid, so it's a proper knotoid. So this problem needs more work. Actually, here is a more complicated knotoid diagram, and we can see from its diagram that the height of this diagram is 2. It needs to be created at least 2 crossings to connect, to tie up these 2 ends here. So the upper bound for the height of this knotoid type is 2. And when we compute the error polynomial of this knotoid, we see that the lambda degree of the polynomial is 1. Therefore, the height of this knotoid type is either 1 or 2. So the question is, what is the height of this knotoid type? Is it really 1? Can we reduce the distance between the 2 endpoints under some isotopy moves and bring it to have height 1? So we need more observation and tools to deduce this question or to answer this question. But I will just finish the review of knotoids and our work with Luke Kaufman at this point, and I will go into the theory of braidoids in the second part of my talk. So the theory of braidoids was introduced by Sofia Lambrou and by myself, and we see some braid-like objects here that are braidoid diagrams. So what we see actually is that some strands interacting with each other and have ends here, and some ends have been denoted by some graphical nodes and some letters at an edge, and some are broken, as we see here, terminate and initiate at any point in the determining region of the diagram. And some ends are numerated by positive integers, as we do for braid diagram ends. So let's go to the definition of a braidoid diagram. A braidoid diagram is a system of finite number of arcs in a rectangular disk in the plane, and we call them, these arcs, the strands of the braidoid diagram B. And we want the strands to have a finite number of intersection points among themselves, among each other, and we want the intersections to be transversal double points, each endowed with under and over data, and we call them crossings of the diagram B. And each strand is naturally oriented downward, have descending direction according to top to bottom direction of the plane, and they have no local maxima or minima, so that each intersects a horizontal line at most once. And the most determining property of a braidoid diagram, as we have noticed from the former picture, is that a braidoid has 2 types of strands: the classical strands that are basically braid strands with ends on top and bottom and numerated with positive integers. And a braidoid diagram has also free strands. A free strand has 1 or 2 ends that are not necessarily in the top and the bottom line of the region of the diagram. And such ends are called endpoints of B, of the braidoid diagram. And they are denoted by graphical nodes and notated by L and H in analogy with the leg and the head of a knotoid diagram. Here we see it better. So they are not really lying on the top and the bottom line of the rectangular disk given for the knotoid, for the braidoid diagram, sorry. So we assume the delta moves, delta isotopy moves for braidoid diagrams. A delta moves is basically to replace 2 arcs with an arc in a triangular region. And in the first instance of this delta move, we observe that the triangular region is free of any intersecting strands. So this is called a planar delta move. We have also some variations of delta moves assumed for braidoid diagrams. We assume the Reidemeister 2 move, which is to replace this two arcs with one arc in a triangular region, but the triangular region intersects with some other strand here. And the third Reidemeister move also can be considered as a variation of the delta moves. We just assume during the delta moves for braidoid diagrams, the downwards direction is preserved, and the braidoid ends that are the usual ends enumerated by positive integers are kept fixed in their position. But we may assume some planar isotopy moves for the endpoints denoted by graphical nodes and given some letters L and H. We can just move an endpoint up or down as long as it doesn't pass through another strand, so as long as it doesn't create a crossing or deletes a crossing. So forbidden moves of knotoid diagrams are valid for braidoid diagrams as well. So in a safe region, we can do this vertical moves for the endpoints, and also we can swing an endpoint to right and to left like a pendulum in the vertical strip bounded by two consecutive braidoid strands enumerated by I and I+1 here. So we don't want an endpoint to exceed the vertical vertical line of a braidoid end. It will be clear in a moment why we just assume a restricted nature for the swing moves. It will be clear after we define the closure for braidoid diagrams. So we say that two braidoid diagrams are isotopic if one can be obtained from the other by a finite sequence of these delta moves and the vertical and the swing moves for the endpoints. And an isotopic class of braidoid diagrams is called the braidoid. We have a special class, subclass, or special class of braidoid diagrams that we call labeled braidoid diagrams. So a labeled braidoid diagram is a braidoid diagram whose braidoid ends, that are also enumerated by positive integers, are labeled with O or U. So to each usual end of strands without any graphical nodes, we give O or U labels that are referring to over or under that will be utilized in the closure of the diagrams. We will see it in the next slide. And we assume the same set of isotopy moves generated by delta moves and vertical and swing moves for labeled braidoid diagrams. And we define a labeled braidoid to be an isotopy class of labeled braidoid diagrams up to this relation generated by the moves. So here is an abstract picture of a labeled braidoid diagram with its endpoints lying in a box, but with its normal ends here aligned in pairs and labels U, O, and O. So we define the closure operation on labeled braidoid diagrams. We close the pairs of corresponding ends with embedded arcs in the plane. And we close it with the rule that if the corresponding ends are labeled with U, we use an underpassing strand to connect these two ends here. And we want the connection arc to remain sufficiently close to the vertical line passing through the corresponding ends. So here, the corresponding ends labeled with O, and we use the connection arc lying sufficiently close to the vertical line determined by the corresponding ends here, and it goes over everything that it meets during the connection. This closure operation induces a well-defined map from the set of isotopy classes of labeled braidoids to the set of isotopy classes of planar multi-knotoids. Apparently, when we close such an object, we will obtain either a knotoid diagram or a multi-knotoid diagram with just one knotoid component. And we can show that it's actually a well-defined map when we consider the classes of the objects, isotopy classes of the objects. So the reason why we consider the connection or the closure takes place in a sufficiently close distance here is that we don't want to meet with any forbidden move between any two connection arcs. For example, I could just close this corresponding ends here by using another connection arc, but comparingly far away from the vertical line of the corresponding ends here. But to turn one resulting diagram to the other one, I need to pass through the endpoint here. So basically, I don't want any point to lie in the region determined by the vertical line here passing through the corresponding ends and the connection arc lying in between them. So I want the isotopy happening in a region clear of any of the endpoints. So here is a picture to show what happens when we close a labeled braidoid diagram and what happens when we don't restrict our swing moves. So let's start with this labeled braidoid diagram. I close the corresponding ends with the given labels here by using underpassing connection arcs. So I obtain this proper knotoid diagram here. We just seen that it represents a proper knotoid with height 1. And in the second instance of the diagram, I actually moved to this endpoint here, braidoid endpoint, slightly to the right, but it passed through the vertical direction, vertical line determined by the second corresponding ends here. So I obtained this labeled braidoid diagram with the same labels, but when we close the corresponding ends with the given labelings here, I obtained this knot type knotoid diagram here, and we can easily show that these are different knotoid types. Actually, we have shown that this is a proper knotoid, and this is just a trefoil knotoid, I can say. So the unrestricted swing moves cause forbidden moves. That's why we restricted them. So the classical Alexander theorem states that any classical knot or link diagram is isotopic to the closure of a classical braid diagram. And we have showed that any multi-knotoid diagram in the plane is isotopic to the closure of a labeled braidoid diagram. So we gave an analogous Alexander theorem for labeled braidoid diagrams by constructing some algorithms to turn a given multi-knotoid diagram into a labeled braidoid diagram. So the idea of these algorithms is to eliminate each up arc that we meet in a given multi-knotoid diagram. An up arc is the arc of the diagram that is directed upwards according to the top to bottom direction of the plane. Here is a picture, a portion of the diagram, and in this portion we see an up arc. And there is a labeling on this up arc. It will be clear in the next slides what it refers to. So we suggest to cut this up arc at a point. It can be any point, but in this picture I cut it in the middle. So when we cut this up arc, we obtain two cut ends, and we just pull the cut ends one to the upper line and one to the bottom line by preserving the vertical alignment with the cut point. And I obtain this pair of corresponding ends here, and I keep the labeling of the up arc here O on the corresponding ends. So in the second instance, it's still not a braidoid strand, as we see. Still, we have this ascendancy here. So to turn these portions into descending portions, we apply delta moves, isotopy moves happening in these triangular regions. So we obtain a pair of braidoid strands eventually. And here in the picture, I also show that by closing the resulting pair of corresponding ends here with the rule of the labeling with an overpassing arc, we can see that this closed strand here is actually isotopic to the initial up arc we started with. We can apply the Reidemeister 1 and then the planar isotopy to turn it back to the initial arc. So this is the main idea of braidoiding moves, braidoiding algorithms. And we observed that if we apply, if we eliminate an up arc of a multi-knotoid diagram in this way, the closure would result an isotopic object to the initial up arc. So braidoiding algorithm has some notions. Let's introduce them. We have the subdivision, the addition of a node, a vertex, or a deletion of it. And we have up arcs and free up arcs. An up arc is the arc of a knotoid or multi-knotoid diagram that is directed upwards with respect to the top to bottom direction of the plane. And an up arc may contain, as we see from the pictures, in the first instance of the picture, different types of crossings. Here, the up arc contains one over crossing and one under crossing. It may contain the same type of crossings, or it may not contain any crossings at all. The up arcs, such up arcs are called free up arcs. And we would like to have our up arcs in the algorithm to have to contain at most one type of crossing. So we will apply some further subdivision on the up arcs to divide them into further up arcs, each containing the same type of crossings on them. Here I put a note here so that we have two smaller up arcs, one containing just the over crossing and the other is containing just the under crossing. For the second instance of the picture, we have just under crossing, so it's not a problem, this subdivision. And also, after doing the subdivision, we will label our up arcs with O or U, depending on the crossing type that they contain. And we have also sliding triangles, right angled triangles with hypotenuse of with the hypotenuse the given up arc, and where the isotopy happens after cutting out the up arc on some point. In this picture, I cut the up arc at its uppermost point P, and I pulled down the ends here to top and bottom lines, and we have the sliding triangle here, which is also intersecting another strand. It may happen, but the isotopy moves allow us to make this portion all descending and to turn it into a braidoid strand. And also I should add that cut points can be chosen anywhere for the algorithm, but we will be choosing them as the uppermost point of the up arcs with respect to our chosen subdivision. And we have also triangle conditions on the sliding triangles. Obviously, we don't want any of the endpoints to lie in a sliding triangle, because otherwise, while sliding this up arc after cutting it at the point P, this portion is, of course, it continues with some other arc here. We don't see it in this picture. So after cutting this up arc at this point, we want to pull it downwards, all this by using all this region here, triangular region. But if we meet an endpoint, then it will obstacle with a forbidden move, and it will change the resulting diagram. So to avoid that, we can apply further subdivision. We can subdivide our up arc to have smaller sub-triangles, sliding triangles, and to leave the endpoint outside of these triangular discs. Also, we don't want any pair of non-adjacent up arcs to be labeled in the same way. Non-adjacent up arcs mean that the up arcs do not contain any common subdividing points, as we have shown in this picture. So we are free to label them in the opposite way, but we are not free to label them with the same label. The reason for that is that we want some algorithms, braidoiding algorithms, free of ordering of elimination, free of ordering for elimination of the up arcs. Here is an obstacle that we meet if we just label these non-adjacent up arcs in the same way. If we decide to eliminate this up arc in the first order and this up arc in the second order, we observe some clasp here, which is avoiding this portion of the second braidoid strand, resulting to be isotoped to a descending strand here. So to avoid such cases, and to be free of ordering of up arcs in the algorithm, we put this triangle condition for the labeling of up arcs. So let's see what goes on for the algorithm. We give two algorithms for turning a given knotoid diagram or multi-knotoid diagram into a labeled braidoid diagram actually. Here we start with this knotoid diagram. We first isotope the neighboring arcs of the endpoints to become a down arc, just to avoid the interfere of the endpoints with the algorithm. So we arrange the endpoints, then we also assume some general positioning arguments on our knotoid diagrams or multi-knotoid diagrams. We don't want any vertical or horizontal arcs for our knotoid diagrams. We can always assume this kind of condition by small perturbations of the diagram, so that we only have up arcs or down arcs forming our diagrams, knotoid diagrams or multi-knotoid diagrams. So we just put dots on the local maxima and minima of the resulting diagram. We put the subdividing points at the local maxima and minima, and if we see some up arcs containing different types of crossings over and under both, we make further subdivision to make up arcs contain just one type of crossing. And according to the crossing type, they contain, for example, here is the up arc containing just under crossings, so it is labeled by O, and here is a free up arc. We are free to label it with O or U. So we apply the braidoiding moves according to the given order. It wouldn't matter if we just assume the second triangle condition on this diagram, in which order we eliminate the up arcs. We wouldn't meet any problem if we assume it. So when we apply the braidoiding moves on the up arcs, we are left with this diagram. We obtain this diagram, and then we isotope some small portions of this diagram to turn it into a braidoid diagram. Here is a Reidemeister 1 move that is available for the resulting tangloid, I can say. And here's an isotopy move that needs to be done to obtain a descending strand, etc. And we keep the labeling on the resulting strands, on the resulting corresponding ends, compatible with the labeling of the knotoid diagram for the up arcs of the knotoid diagram. And in the second algorithm, it's more like a topologist algorithm. We make some rotations for the crossings of the given diagram if the crossings contain one or two up arcs. Here we start with the same knotoid diagram example, and we see that the first, the third, and the fourth crossings contain up arcs. Actually, the first contains just one up arc, but the fourth and the just the fourth contains two up arcs. So we rotate these three crossings here 90 degrees or 180 degrees to turn the up arcs into down arcs. The aim for doing this is to clear up the crossings from any of the up arcs, so that we are left with up arcs containing no crossings, as we see from this picture. So we label the local maxima and minima again of the resulting diagram, and we see that local maxima and minima divides just the up arcs, free up arcs, and the down arcs. The free up arcs are labeled in the homogeneous way with the same label. We are free to do that for free up arcs. And we give an order, and we apply the braidoiding moves to obtain this braidoid diagram with labels on its corresponding ends. This is a more, this algorithm is more flexible, and it results in a more homogeneous object with the same labels in its corresponding ends. And also, we can observe that there is a bijection between the set of braidoids and the braidoids with its ends labeled by U, just only by U. And with this algorithm, we can define uniform closure. When we are given a braidoid diagram, we can think that its ends are labeled only with U, and we can assume an underpassing closure with, for each of the pairs of corresponding ends in the braidoid diagram. And we have a sharpened version of the Alexander theorem of the braidoids for this. Any multi-knotoid diagram in the plane is isotopic to the uniform closure of a braidoid diagram. So with this algorithm, we are getting rid of the labeling, actually. When we are given a braidoid diagram, we can apply the rotation to the crossings, having up arcs in it. And so we are left with the diagram, an isotopic diagram, with free up arcs, which can be labeled in the same way. And we obtain a homogeneous labeled braidoid diagram, which can be considered as just the braidoid diagram without any labelings on it, with the bijection map in between, so that it can be considered as a sharpened version of our theorem, this result. So we have also proved a Markov theorem for braidoids. Actually, let's remember the classical Markov theorem. The statement says that the closures of two braid diagrams, represent isotopic links in the three-dimensional space if and only if these braids are equivalent as braids up to braid isotopy, and with these two algebraic operations called conjugation and stabilization. This is a well-known result for knot theorists, at least. And in the beginning of 90s, Lambrou gave a one-move Markov theorem for braids and links by defining L moves that I will show in the next slide. She shows that there's a bijection between the set of L equivalence classes of braids and the set of isotopic classes of oriented link diagrams. So L equivalence covers all these moves and braid isotopy in her statement. So let's see what a L move is. Here in the middle, we saw a portion of a braid diagram, or we can assume it to be a portion of a labeled braidoid diagram for our aims. And we just pick an interior point on it, and we can apply either an L under move or L over move, move, that is to cut the given portion of the strand at the chosen interior point, and to pull the resulting ends to top, to bottom, and to the top line of the braid or braidoid, by preserving the vertical alignment with the cut point here. So the L under move applies this cut operation and pulls the resulting ends under everything, and the L over move just pulls everything over the rest of the diagram, so that the resulting braidoid diagrams are labeled with U and O accordingly to the type of the L move that we are applying. So this is an L move is adding a braidoid strand, a labeled braidoid strand to our existing diagram, or it deletes braidoid strands if it just define the inverse operation here. So here's a small observation also. When we close the corresponding ends, the resulting corresponding ends with respect to the rule of closure with an underpassing connection arc here, we can see that this closed strand here is isotopic to the initial portion of the braidoid strand or braid strand. We also have fake swing moves for labeled braidoid diagrams. We are trying to define an equivalence to construct a Markov theorem for braidoid diagrams, for labeled braidoid diagram. So we have L moves for this, we have seen, and fake swing moves. Fake swing move is actually an unrestricted swing move happening on a labeled braidoid diagram. Example, here is a picture. The endpoint here exceeded the vertical line of this corresponding ends here. This is not allowed in braidoid isotopy, but we can see that it makes no harm when we take the closure. When we close up the corresponding ends here, according to the labels, we can see that there will be a Reidemeister 1 move available for the resulting closed object. So we call this kind of unrestricted swing moves that results in a knotoid isotopy when we take the closure of the braidoid diagram, fake swing moves. And the L moves together with labeled braidoid isotopy and fake swing moves generate an equivalence relation on labeled braidoid diagrams that is called L equivalence, just as we said. And we have proved that the closures of two labeled braidoid diagrams are isotopic multi-knotoids in the plane, if and only if labeled braidoid diagrams are L equivalent. They are related to each other by L moves, L over, L under moves, or the deletion of these moves, and also fake swing moves. So to prove this analogous theorem, analogous Markov theorem for braidoids, we have already observed that the closure induces a well-defined map from the L equivalence classes of labeled braidoids to the multi-knotoid set. We have seen from the former slide, this slide, that when we apply an L move on a portion of a braidoid strand, the resulting pairs of corresponding ends can be closed in the with respect to the given label here. And when we close it, we turn back to the initial portion of the braidoid strand up to isotopy. So this suggests us that this the closure gives us a well-defined map from the L equivalence classes of labeled braidoids to the isotopic classes of multi-knotoids. And for the other side of the statement, we need to show that the braidoiding algorithm induces a well-defined map from the set of planar multi-knotoids to the L equivalence classes of labeled braidoids. So for this, we need to check two things, static things and moving things. I can separate in this way. The static things for showing this statement can be shown by proving that this braidoiding map is well defined under the choices done for applying the algorithm, such as subdivision, labeling of the free aparts. We say that this is the static part of the proof because we just assume the given knotoid diagram fixed for the first braidoiding algorithm, and choices for subdividing it and labeling the free aparts is not related to the isotopy moves of the diagram. So it's not really moving, these choices. And the moving part contains to show that this map is well-defined under the isotopy moves for knotoid diagrams, including the moves displacing the endpoints. So let's start with the lemma. So we can easily show that adding a subdividing points to our up arcs in a knotoid diagram results in L equivalent braidoid diagrams. So here is again a portion of a knotoid diagram, which is an up arc. and it is labeled by O. And here is, to make our life more difficult, an endpoint of the knotoid diagram lies here, and the vertical line passing through it intersects with the up arc. And I first apply the braidoiding move by choosing the cut point at the point P here. So I obtain this pair of braidoid strands here. And then I decide to subdivide my up arc further. Here I put another subdividing point, P1, and I decide to apply the braidoiding move, two braidoiding moves at P1 and at P, and I obtain these braidoid strands here. So the reason why I chose the subdividing point here is that I wanted it to remain on the left-hand side of this vertical line here, so that the subdivisions and the braidoiding points take place in different sides of the endpoints. So that was the important point for knotoids, the endpoint locations. So we see that from this picture to this picture, we have an over move that can be applied in a neighborhood of the point Q here. When we just apply an L over move here, cut this strand here and pull the resulting ends up and down, going over everything, I obtain this braidoid strand here. So we see that the subdivision is transformed as an L move under the braidoiding move. So also we have said that labeling the free up arcs in either O or U way do not matter for the resulting diagram. Actually, it's changing the labeling of a free up arc results in L equivalent braidoid diagrams. Here, I decide this up arc to be labeled with U, and I apply the braidoiding move at the point P, and I obtain this diagram here, and I obtain one more L over move at the neighborhood of the point P, and I obtain these strands here, this collection of strands. Then I could also start by labeling this free up arc with O. Since it's a free up arc, I can change the labeling, we said. And I apply the braidoiding move at the point P, and I go to this diagram. I obtain this diagram, and from this diagram to this diagram, I have a deletion of an L under move to delete this strand here and to be left with just this pair of braidoid strands labeled by O in the corresponding ends. So again, up to L equivalents, changing the labelings of free up arcs wouldn't matter. And from these two lemmas, we can conclude that we can deduce that if we are given any two subdivisions on a fixed knotoid diagram with any admissible labeling that's also satisfying the classical triangle condition, the second triangle condition, then the resulting braidoid diagrams are L equivalent. And let's go to the moving part of the statement, or the proof of the statement. I will just show that under the first Reidemeister move, we will obtain L equivalent diagrams when we apply the braidoiding move on our knotoid diagram. So the lemma states that knotoid isotopy moves on a knotoid diagram transforms to L equivalence moves under braidoiding moves. So here is a Reidemeister one move taking place, and I delete the king here. I'm left with this up arc labeled by O. So I just obtain an up arc in between these two subdividing points. And if I apply a braidoiding move over this portion of the diagram of the knotoid, I obtain this diagram here. I can say this is a tangoid diagram. And then I obtain the isotopy to correct this triangular regions. And I obtain these pieces here. And if I go in this direction, if I apply braidoiding move over this up arc, I obtain this pair of braidoid strands here labeled by O. So to go from this diagram to this diagram, and so this diagram, I need a deletion of an under move to delete this braidoid strands here, and an isotopy just to shrink this strand here a little bit to back. So the other Reidemeister moves on knotoid diagrams can be shown in the same similar way, that they are transformed into L equivalence moves containing L moves, addition of L moves, deletion of L moves, and also isotopy of braidoids. And also we have some planar isotopies that look innocent, but they can be nasty since we can move an endpoint with respect to move an endpoint of a knotoid diagram with respect to a cut point for the braidoiding move. So let's swing the endpoint of the knotoid diagram with respect to this upmost point, the cut point of the up arc here labeled by U. And in the first instance, it's here, and I apply the braidoiding move. I apply this diagram here, where the endpoint the arc of the endpoint crosses over the resulting braidoid strand. And in the second instance, after the swing move, we take the endpoint here and we obtain this piece of diagram under the braidoiding move, where we don't observe any crossing here. Actually, this is really like, this resulted in a forbidden move for the resulting braidoid diagrams. To take the endpoint from here to here, we need a forbidden move. But we call such moves as, we name them as fake forbidden moves, because actually if we connect the corresponding ends, the resulting connecting ends from resulting diagrams, for resulting diagrams, we obtain isotopic objects. Here we connect the corresponding ends here with an underpassing strand, and we can see that we will obtain a Reidemeister 2 move available to shrink down the resulting closed strand, and isotopic to the closure of these strands here. So we call these fake forbidden moves because they are forbidden moves on the labeled braidoid diagrams, on the braidoid diagrams in general, but they result in isotopy moves on the closure for knotoid diagrams. So we need to show one more thing, because we say that planar isotopies displacing the endpoints result in L equivalent braidoid diagrams. L equivalence was including just L moves, isotopy moves, and also fake swing moves, but we observe a fake forbidden move here for planar isotopy transforming under the braidoiding moves. So we have also shown that fake forbidden moves are generated by L moves and planar isotopy, so we are safe to define the way that we define L equivalence just covers everything. And the last step is that after showing all these lemmas and observations, we can deduce that the braidoiding map induced by the braidoiding moves is well defined. And it's not hard to see that the braidoiding map and the closure map act as inverse maps to each other. And this completes the proof of our theorem. So the results that was explained today by myself are from these reference articles. Tribe's article, Knotoids we see virtual knot theory. Throughout our study of knotoids, we used it a lot, virtual knot invariants and virtual knot concepts. The height results are from new invariants of knotoids with Luke Kaufman, and braidoid results you can find it in knotoids, braidoids, and applications with Sofia Lambropoulou, and also recently an accepted publication, Braidoids, that will be appearing in the Israel Journal of Mathematics. So thank you very much for your attention. it was really an interesting experience. I hope it works for all of us. I hope it was helpful for understanding these concepts for you. So take care.